Hi, everybody. Um, it's good to be here with you guys on the internet. Excited for our labs next week. This week, we're going to be talking about chemistry. And we've got a couple of little beautiful creations of the universe here in front of us. These are incredible. These are snowflakes, obviously. And I find them fascinating because they share a common similarity, and yet they're all unique. So the common similarity that all snowflakes share is that they have 6 sides. So you can see this. So we have 1, 2, 3, 4, 5, 6. They are all 6-pointed. And yet they all have a unique shape. Pretty crazy. So those are the rules. So we're going to explore the rules that govern snowflake shape. And you may be like wondering, what the heck does this have to do with biology? It'll all make sense here in a second. So how does a snowflake have this regimented 6-pointedness and also this unique shape, a unique individual shape? We're going to talk about that. So water itself, the water molecule, builds that unique shape. So it's the actual chemical and physical properties of that water molecule. So if you look at a water molecule, if you remember this, it kind of looks like a Mickey Mouse. I have it upside down here. This would be the oxygen atom. These would be the hydrogen atoms. And the oxygen has a slight negative charge, and the hydrogens have a slight positive charge. This makes them like little magnets. Water molecules, I call them little sticky Mickey Mises because they like to stick to each other. And when you freeze them, the water molecules will arrange in this 6-sided shape. They will form this hexagon-like shape. Boom. And that's how a snowflake gets its 6-sidedness. So 1, 2, 3, 4, 5, 6. 6 little sides, points would come out of the snowflake because of the physical properties, the way this is bent and the way it has these charges. When you freeze it, all these water molecules line up and form this beautiful, what's called a crystal lattice. A crystal is an organized structure at the molecular level, repeated and organized. So that's how snowflakes get their 6-pointedness. It's from the information stored in the physical and chemical properties of the water molecule. And that's why it never changes, because it's boom, that information is stored in that water molecule. Like if you were to take this hydrogen and maybe it was to actually be over there instead of right there, you would have a completely different structure for frozen water. Water is a very, very special molecule. Okay, so now how do snowflakes get their unique shape? So here we got a snowflake, a little dust particle in the sky. It's up, it's cold, water molecules start to accumulate on it, and they form this 6-sided shape. Water molecule is freezing and becoming a snowflake. It's becoming a solid. It's going from a vapor, water vapor, into now a solid. It's up high in the atmosphere. It's very cold up there. Let's say now it's falling down through the sky. And when it gets closer to the Earth, it's going to be a higher temperature. So there's going to be some melting that occurs. And so now some of that snowflake is going to melt away. And then maybe the wind blows the snowflake back up to lower temperatures where it's cooler up higher. And now there's more freezing occurring. Crazy. So every snowflake gets its unique shape through the path that it takes through the atmosphere, through its life as a snowflake. And no snowflake will have the exact same trajectory through the atmosphere. It'll enter different temperatures, go higher, go lower, float around at this kind of stable elevation for a while, and then it'll fall, and then it'll rise. And so it's its unique path through life that gives its unique shape. So those are the two things that govern a snowflake shape. Pretty crazy. Okay, well, life is the same way. You may have heard of this molecule. It's called DNA. We store information for building us within our DNA. And DNA is made out of molecules called nucleotides, and they give it its unique shape. That DNA is converted into something called RNA, which acts as a messenger to then build something called proteins. So this is our long-term storage, short-term messenger, and then these are our little machines, little nano machines that build us up. And these guys are made out of little things called amino acids. And these amino acids give them their structure. So here, just like a snowflake is built out of water molecules but can have this big, unique, interesting, rule-based shape, our DNA and our proteins are also similar. And these proteins are little nano machines that do jobs. We've all heard the word protein. It's chicken, it's meat, right? It's also soy, it's also nuts, it's also dairy. All have high sources of protein. But look at these things. What I'm showing you here, this is a protein. You're going to see DNA and protein here, and you're going to see this little protein here. Look at these things. They are machines. This is all protein here. This is literally a walking protein. It walks with feet. These are what make your energy. So these shapes built out of these molecules allow them to perform specific functions. And the same is true at the cellular level. So when we're talking about molecules, this would be like at the snowflake level, a little bit smaller usually. But now all of that information stored in DNA and stored in the proteins and all of that, now based on the environment that those cells live in, and this is true, that's going to dictate their function and their shape. So for example, these are all different shaped cells. If you take a cell and you put it in a soft environment, it will become a nerve cell. What? If you take a cell and put it in a medium stiffness environment, it will become a smooth muscle cell. And if you take a cell and you put it in a stiff environment, it will become a bone cell. So just like snowflakes, our biology has these rules that give it some unique properties that are true for all cells. But then it's its environment that then dictates not only its shape, but also its function. And so both snowflakes and life follow the same rules. Living organic material follow the same rules of having information stored within them, but then being molded by their environment. And this is true for every human being too, right? If it's true for cells, it's true for humans, right? You could take two twins, which are genetically identical, raise them in different environments, and you will see the differences. Raise one in a terrible, kind of unloving environment, just like the rats, versus a very loving, supportive environment, and you will see those differences accumulate not only in that person's abilities and desires and wants, but also in their biology. The level changes in stress, maybe they'll become addicted to things, so on and so forth. So you have this information stored within you, but you also have this unique path that you take through life that makes you who you are. Just like a snowflake. Okay, that's that first little lecture, and now we'll get into that's like a little kind of big philosophical look at why are we talking about chemistry in a biology class? Well, that's why. You can't have biology without chemistry. Biology is a mushing together of chemistry to make us, to make this thing, to make this beautiful little kitty man. This is a real cat. It's actually not, but I made this when I was in middle school or something. This was my cat Vader. He's pretty nifty. He glows in the dark. Okay, bye. Snowflakes.